In today's lecture, we will see design of belt drives. Belt drive is used to transmit power through long distances. In this case, driver and driven pulleys need to be rotated in same direction. So they are connected by a flat belt. This is a belt. And such an arrangement is called an open belt drive. We have another type of belt drive in which the driver pulley and driven pulley needs to be rotated in different direction. Such a drive is shown in this figure, and this type of drive is called cross belt drive. Depending upon the distance through which the power has to be transmitted, different types of belts can be used, and they are classified as flat belt, V belt, round belt and timing belt. Flat belt is generally used for transmitting power through 5 to 10 meters distance. If the distance is more than 10 meters, we use a round belt, and if it is less than 2 meters, we use a V belt. Now, the timing belt, which is commonly used in automobiles, has an advantage that it has 0% slip, or it is called a positive drive. Now we can see types of belt drives. We have already seen open belt drive, where both are rotating, both driver and driven pulley will be rotating in same direction, and such belt drives can be used in automobiles. Then similarly, we have flat belt drive used in cross belt drives, where the pulleys rotate in opposite directions. The basic principle of flat belt drive is that it works on the principle of friction. The friction between the driver pulley and the belt drives the driven pulley. So when the driver rotates, in this case the driver is rotating in clockwise direction, so the entry side will be the tight side, and so this is the entry side, and this is the exit side of the driver pulley. So on the entry side we have the tight side, and on the exit side we have the slack side. Whereas for the driven pulley, this is the entry side. Entry side. Driven pulley, entry side will be slack side, and exit side will be the tight side. So the tight side tension will be higher when compared to the slack side tension. This is similar to what we see in a bicycle. Whenever we ride a bicycle, there are two sprockets which are connected by a chain. We have the pedal. When we rotate the driver pulley in anti-clockwise direction, we can see that the upper side will be tight and the bottom side will be slack. This we can see in a bicycle. So we can say that this is the driver pulley. On driver pulley, entry side will be tight and exit side will be slack. Whereas for the driven pulley, it is in the reverse direction. Entry will be the slack side, and exit will be in the tight side. Now, what happens when slip occurs? Whenever there is insufficient friction between the driver pulley and the driven pulley, the driver pulley will rotate without carrying the belt with it. So what happens? There will be some slip, there will be some relative motion between the driver pulley and the belt, such that the driver pulley will be rotating without carrying belt with it. If it doesn't carry the belt with it, the driven pulley cannot rotate. So there will be relative motion between the pulley and the belt, and such a case is called slip in the belt drives. So we can say insufficient frictional grip between the belt and the shaft, or between the belt and the pulley, causes the forward motion of the belt without carrying the driven pulley. So the driver pulley and driven pulley will be having different speeds or of course it will be having different speeds, but it doesn't have, it will, driven pulley will not be reaching the required RPM, or there won't be any much power transmission compared to the required value. Such a case is called slip of the belt, and usually it is denoted by slip is denoted expressed as percentage. Now there is another one called creep. When belt passes over a pulley, when it goes through the tight side, it having extension, it will extend, its length will increase or it elongates, and whenever it goes to the slack side, it will contract. Such a case will result in the creep of the belt drive. And due to this changes in length, there will be a relative motion between the shaft and the belt surfaces, and this relative motion is called, which reduces the efficiency of power transmission. Now we can see how to design a belt drive. So in a belt drive, there will be a driver pulley and a driven pulley of different diameters D1 and D2. They will be connected by a belt drive. So we have to find all those dimensions: diameter of the larger pulley, diameter of the smaller pulley, center to center distance, angle of contact for the larger pulley theta L, and for the smaller pulley that is theta S, angle of contact between the belt and the pulley. Then we have to find the length of the belt, what is the coefficient of friction, then width of the belt. Normally we take a rectangular section, thickness T and width B. We have to find these dimensions. We have to find this area, we have to find these dimensions. Then, as we have already seen, we have to find the belt tensions. Maximum tension, that is the tight side tension, is denoted by T1, and slack side tension, which is lower value, slack side tension T2, and there should be some initial tension, that is denoted by initial tension, that is denoted by TO. We can see all this, how to find all this in a problem. A horizontal drive is required to drive a compressor by an electric motor. Select a suitable belt drive. Power equal to 6 kilowatts. Service factor equal to 1.2. Whenever power and service factor is given, we have to multiply power with the service factor for the use in the calculations. Slip equal to 2.5%. Motor rotates at 1400 rpm. Compressor rotates at 500 rpm, smaller value. Working stress equal to 2 megapascal, that is for the belt maximum stress which the belt can withstand. Mu equal to 0.35. Joint efficiency equal to 90%, and density equal to 1000 kilogram per meter square, that is the density of the belt material. First step in the design is to select the diameter of the pulley. So we have this equation from page 292. Equation 14.9a, I can find the smaller diameter of the smaller pulley. I can take this equation. So there is a range 525 to 630. Here I am taking 630 root of P by, where P should be the maximum power. Whenever service factor is given, we have to multiply the nominal power with the service factor to apply in this equation. Then N is the speed in RPS. So we can substitute all these. So I can write P equal to maximum power, P equal to 6 kilowatts multiplied by service factor CS multiplied by nominal power, equal to 7.2 kilowatts. This is a numerator. Now 2 pi N max. N max is the speed of the smaller pulley, because smaller pulley will be having higher RPM. N max will be the speed of the smaller pulley. it is given speed equal to 1400 rpm. So n max n equal to 1400 by 60. We have to substitute in rps, that will be about 53.33 rps. Sorry, 23.33 rps. 33 rps. I can substitute in this equation. So taking this equation from 14.9a, I can write small d equal to, taking the higher value 630 root of power equal to 6 into 1.2, 7.2 kilowatts. I have to substitute in kilowatts, divided by 2 pi into n max equal to 23.33. I can get this value to 130.71 millimeter, which is the diameter of the dia of the smaller pulley, small d. Now I need to get the diameter of the larger pulley. Diameter of the larger pulley can be found from equation 14.9b. Equation 14.9b. Capital D equal to 1 minus epsilon small d I, where epsilon is the percentage slip. Given percentage slip equal to 2.5 percentage, 2.5 percentage equal to 0.025, 2.5 by 100. So 2.5 by 100 equal to 2.5 by 100. Small d is known, 230.71. I is the transmission ratio. I equal to N2 by N1. I equal to maximum speed 1400. That is the speed of the motor, divided by speed of the compressor, that is 500 rpm. 500 rpm speed of the compressor. So this value will be equal to 2.8. We will get capital D equal to 629.86. Now we need to standardize these values, for which I have this table from table 14.13 page 313. My value was 230.71 for the smaller pulley. So our next value will be 250. This value I take for smaller pulley, that is small d, and the value of capital D was 629.86. 629.86. So I will take the next higher value from this table. So my value will be equal to 629.86. I can take 630 diameters. After 629, and next higher value will be 630. So this value I set as a standard dia for capital D. So standard dia small d equal to 250 mm and capital D equal to 630 mm. For further calculations, we will be using these standard diameters. Now we can find the center to center distance. Center to center distance between the pulley. Okay, so we have the belt drives. We have found the value of small d and capital D. Now we can find this center to center distance. Center to center distance denoted by C. Very simple equation. C equal to, again I have this equation, 1.5 2 into d plus d. I will take this equation 14.2d. C equal to 2 into capital D plus small d equal to 2 into capital D was equal to 630 and small d was equal to 250. I will get that value C equal to 1760 mm. This completes our Next, now we can find the length of the belt drives. Length equal to, so we have the equation, it's an open belt drive, so I have this equation where I don't know the value of theta L and theta S. So the next step will be equal to find the angle of contact, theta S and theta L, where theta S and theta L are the angle of contact. We can see that for the larger pulley, this is the angle of contact, that is theta L, usually greater than 180 degree, and for the smaller pulley this will be the angle of contact, theta S, usually less than 180 degrees. We can substitute in this equation where capital D equal to 630 mm standard value, small d equal to 250 mm, and C equal to 1760 mm, as we have shown. Substituting these equations, I can get the value of theta S and theta L. Theta S equal to 167.6 degrees and theta L equal to 192.39 degree for the larger pulley. After finding theta S and theta L, we can find the length of the belt. Substituting in this equation, equation 14.2b in page 290, I have this equation. Substituting this value, where C is known, capital D, small d, all those values are known. Here we have to substitute theta L and theta S in radians. Whenever we have the angle given without any trigonometric function, it should be in radians. For example, length of an arc, that equation equal to r theta. It doesn't have any trigonometric functions, sine, cos or tan functions. In such values, theta should be in radians. That same applies here also. Here theta L and theta S exist without any trigonometric function, so theta L and theta S should be substituted in radians. So substituting those values, I will get L equal to 4922 mm. Now we can find the minimum friction. Whenever we have a flat belt drive, the transmission depends upon the lower values of mu and theta. So mu theta will be equal to, for the calculation, mu theta should be taken as the minimum of mu s theta s and mu l theta l. In this case, given mu s equal to mu l, friction is same for both the pulleys. Mu s equal to mu l equal to, that value was given in the question, equal to 0.35, and theta s is less than theta l. I can take mu theta equal to, mu theta will be equal to mu equal to 0.35 multiplied by theta s. Theta s was equal to 167.6 degree. I had to convert into AC into pi by 180. So mu theta will be equal to 1.0238. After finding mu theta, then I can find the dimensions of the belt. I have this equation. Here we have to use this equation, power equal to BTV by this equation, where we have an additional term, joint efficiency, which is not given in the data book. You should add that also when we substitute in the equations, where B and T are the cross section of the belt drives. B is the breadth, T is the thickness, V is the velocity. It should be substituted in meters per second. So I can write velocity equal to pi dn by 60 pi d n by 60. For the smaller pulley, pi into diameter was equal to 250 mm. I have to substitute in meters, 2.25 meters, that is diameter in meters, multiplied by its velocity 1400 rpm divided by 60. You will get velocity equal to 18.32 meters per second. Now, given sigma d equal to the maximum stress the belt can withstand equal to 2 Newton per mm square, 2 megapascal, sigma d equal to 2 megapascal, which is same as 2 Newton per mm square. 1 megapascal is same as Newton per mm square. So we got the value of velocity and sigma d. Then W is the weight density, which should be substituted in Newton per meter square. Here we are given density equal to 1000 kilogram per meter square. So my weight density will be 1000 into 9.81. So it will be 9810 Newton per meter square. So we have found the value of W also. G equal to 9.81 meter per second square, and mu theta is also known. I can substitute all these values where power should be in kilowatts. So I can substitute all those values. So G equal to 9.81 meters per second square, mu theta equal to 1.0238, and given joint efficiency equal to 90%. So 90% will be equal to 0.9. 90 by 100 equal to 0.9. Now we can substitute all those values in this equation. So power equal to value of power transmitted equal to 6 kilowatts. Power equal to 6 kilowatts. Beat is unknown. Velocity equal to 18.32, that much meters per second. Sigma d equal to 2 Newton per mm square. W is the weight density 9810 Newton per meter square. G equal to 9.81 meter per second square, and e raised to mu theta will be equal to e raised to 1.0238, and e raised to mu theta will be equal to 2.78. After substituting all those values, we will get the value bt equal to 369.46 millimeter square. Here we have two unknowns, both b and t are unknown. So I will assume one of those values. Assume thickness t equal to 2 mm, I can get b equal to 184.73 mm. Now our next step is to find the belt tensions. We have seen there is tight set tension T1 and slack set tension T2. Whenever the weight density is given, we have to consider the centrifugal tension also. So centrifugal tension equal to WBT V square by 10 to 6 G. So first we will find the centrifugal tension. Centrifugal tension equal to I will write this equation, WBT V square by 10 raised to 6 G, where G equal to 9.81 meter per second square. All those values are known. Velocity equal to 18.32 meters per second. W is known, that is the weight density 9810 Newton per meter square, and BT value equal to 369.46. Substitute millimeter square. Substituting all those values, I will get Tc equal to, I'll get Tc equal to 124 Newton. Now we need to find the maximum and minimum tension, that is tight set tension and slack set tension. To find T1 and T2, we have these two equations. Power equal to T1 minus 14.5 A and 14.3 C. Here we have two unknowns, T1 and T2. So we can substitute in these equations. Substitute in the second equation, I can write T1 minus 124, that is Tc, by T2 minus 124 equal to e raised to mu theta 1.0238 equal to 2.78. Substitute in the first equation, I can write power equal to, power in kilowatts, 7.2, power equal to 7.2 equal to T1 minus T2 into velocity, that was equal to 18.32 divided by 1000. From these two equations I can solve. I will get T1 equal to 738 Newton and T2 equal to 345 Newton, and initial tension can be found from this equation, equation 14.8. From 14.8 we can find that equation, root TO equal to root T1 plus root T2 whole divided by 2, that will be equal to 523.04 Newton. So only thing we have to consider is that in all the cases power should be equal to nominal power multiplied by service factor 6 kilowatts. Okay, made a change, 6 kilowatts into 1.2. In all the cases power should be substituted in with maximum power. We can get all those values. Okay, thank you for listening. Have a great day. Thank you.